So this talk is about software-defined networking at the tactical edge. And all these slides are available even right now at this URL, sdnbell.htm. And if you have internet, you can just go to rajjain.com, go under talks, and then this is the talk, which is basically the second one, because I have given 2 talks this morning. So I gave 1 talk this morning, and this is second talk. So it's all there. All the slides are there, so you don't have to take any notes. And second thing is, how long do I have?
How much time? As per you, 1 hour to 1 hour 15 minutes.
1 hour 15 minutes. Okay. So basically, I will do that in whatever time you need, because people have to go home too. Second thing is that please ask questions right during the talk. Okay. If it is not clear, if you have some comment, agreement, disagreement, anything, please during the talk. You don't have to wait until the end. I will manage my time. I have the timer right here. All right, so I'm going to talk about what is SDN and what it is not. And this is a very debatable topic. SDN has been around for 5-6 years. A lot of people know what SDN is, but there's a lot of confusion what it is and what it is not. Second, I will talk about what is happening now in networking, and then take you from software-defined networking to software-defined intercloud, and then intercloud applications. So what SDN is not? I don't know. How many people know SDN, by the way? 1, 2, okay. So let's say 25% of the audience. And a lot of people will say SDN is OpenFlow, and if you don't know OpenFlow, don't worry about it. Some people will say standard southbound API. Some people will say centralization of the control plane, and some will say it is separation of control and data planes, right? And all of these are wrong. And this is a well-known story as to everybody sees a piece of it and thinks that is what it is, the whole thing, but the whole thing is very different. All these 4 are mechanisms, how to do something. They are not definition of anything. So SDN is not about a mechanism, it's a framework, and so there are many ways to get there. Basically, when we want to do something, we rather tell, well, that's our goal, and then people can find their own way to get there. But if you tell them, no, this is the path, then they will not be very innovative, right? So these are all the paths to get there, maybe, but the goal is different. So there are 3 features that define SDN. First is that we basically take out the hardware. Nowadays, the hardware has become so fast that if you take a standard Intel chip, ARM chip, Atom chip, whatever, they're very powerful, and so we don't need very specialized hardware for anything, almost anything. Okay, I mean, there are always exceptions. So we can take a standard hardware and then provide the software API, the application programming interface, and so everything is programmable. So shifting away from the static manual operation to fully configurable and dynamic programmability. So basically you can change everything, whether it is a router, whether it is a switch, whether it is a server. The hardware is same, just the software is different, and then another thing is that you can program it remotely. Centralized control of policies. And another thing is that we don't have one thing to program, we have to program hundreds of things, hundreds of routers, thousands of routers, and so it will be good if we can do it from one place. Okay? So centralized control of policies. So this is a guy who is a network manager, and he is managing all these routers and switches. He could sit here and then change the policies. A lot of people confuse policies for control. So they will say centralized control plane, which it is not. So this is why I want to say that clearly, is that SDN is centralized control of policies. Once you tell the policies, and I will explain this a little bit more in the next few slides, if you tell the policies, then people can implement it in their own way, right? But if you tell them exactly what to do, then that is basically, then again, no room left for anybody to do differently, right? Okay. So software-defined has actually become very, 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 very popular, and everything is software-defined. If you're designing anything, you have to put the word software-defined in front of it. You can have software-defined networking, software-defined data center, software-defined storage, software-defined compute, software-defined infrastructure. So like this cartoon says, everything but the kitchen sink is now software defined. Okay? And it won't be very late that tomorrow when you get a kitchen sink, it says software defined kitchen sink because you can control it remotely and do whatever you want to do. It's Tsunami. So what does software defined do? If you make it software defined, what do you get? First thing you get is the programmability. You can change the behavior on the fly. Automation, you can basically automate things. You can write a program to control the program. And so human beings don't have to sit down and press the keys. Orchestration. So what does orchestration mean? Does anybody know? How many people know what is orchestration? No, but basically all of you know orchestra. When you go to orchestra, there is a director who has a stick in his hand and then he waves it like this and suddenly the music changes. Right? And he says like this and then down, and then everything starts again. So that is called orchestration. That with one stick, he can control the music of hundreds of musicians sitting in that room. Same thing, orchestration in this means is that sitting at one place, you can control thousands of routers. Okay? And you say, no, our policy in the morning was that people from China should be allowed, and now in the evening, we don't want them to be allowed. You just change it and everybody will implement it. Right? You don't have to go to each person and tell them individually because it's all software defined. And there are chairs in the front if you want to come for those guys that can do it. And then visibility. So basically, because everything is software defined and everything can be controlled from the center, you can monitor them from the center so you can see what is going on in the whole network from central place. Performance. And you can optimize the performance, virtualization, and that is the key. Basically, you can virtualize the devices. You can use, so with virtualization, what happens is, with physical resources, you have to, if you need two of them, you need to buy one more. With virtualization, you don't need to buy one more, you just make two out of one. Like virtual machines. And if you have one computer, you can take 2 VMs on that, you can put 3 VMs on that. So virtual things are very easy to create. Virtualization. Dynamic scaling, and then you can change the size and the quantity because they're virtual. Multi-tenancy, many people can share it. So if we have a software-defined network, we can say, well, if you get the traffic from X, from this journal or from this mission, do it this way. If you get it from that mission, you do it other way. So basically multiple tenant, basically multiple people can use the same facility. And they can have their own policies, they can have their own service, whatever they want, right? Service integration basically means that you can have many services and they can be combined because now everything is software defined. Openness is that now because as the SDN is coming in, we are getting standard software. So you take the standard, as you will see in a minute, some controllers, and you can get the open software. So everything is becoming open. Open means that you get the source code, open source, and you can change it the way you want it. And so the old days of getting the source code from, you never got the source code from IBM, let's say. You got the software from IBM, which is closed source because source is not given. Now you get the open source everything. Anyway, so the SDN is very beneficial. The question is why we are centralizing. So remember how the internet came about. In 1968, the United States was afraid that if the Russia were to put a bomb on AT&T headquarters, they won't have any communication. Because in those days, all the lines from every building went to AT&T and from all AT&T quarters to their headquarters. And so if you want to talk from here to there, your voice will go all the way from AT&T headquarters to some other place. And if you destroy that center, then nobody can talk to anybody. Single point of failure. So they told 4 universities, look, we want you to design a network that will never fail even if there are 100 bombs which are put on 100 buildings. So they designed internet, which is packet switched, where every router is independent, totally distributed, algorithms are used. And so if you destroy 99 routers, the one will still be working trying to find the optimal path for you. Right? So we designed a distributed system, but that was 40 years ago. Now we are saying that if you have 100 routers, connect them to one place. So why are we doing that? Suddenly there is a change in thinking that centralization is good. And I will tell you why it is good. is that centralization means that when there is some change, it is very easy to fast respond. There is fast response to changes. Basically, let's say I get sick and I'm working for a company. There are two ways to do it, centralized or distributed. In the centralized manner, I just call my boss and say, look, I'm sick today. And the boss will say, don't worry, and I will assign your task to somebody else. And we are done. In the distributed manner, I have to call 15 of my friends and say, well, I'm sick, I'm sick, I'm sick, I'm sick. And then they call their friends and say, Raj is sick, Raj is sick. And by the time everybody knows, I'm back to the work and saying, look, I'm okay, I'm okay, I'm okay. And so it takes quite a bit of time for the information to go everywhere. So the current protocols, which are OSPF and OP and everything that you learn about BGP, they take quite a bit of time to become, basically to implement them, or what we call to stabilize. And so that is not acceptable anymore. Previously it was acceptable in those days, in 40 years ago, but today we want instant satisfaction. If we want to get something done, we want it right away. And so we cannot have something, wait for 10 minutes or 5 minutes to stabilize. So that is the thing. This is fast consistency. When you want something, the center knows what is the right thing and tells everybody. In this case, it takes time. Not less overhead, and because you just tell your boss, so the overhead is very little. Here, there are lots of messages going around. And this is only one problem. There is one problem with the center, there is a single point of failure. That's where we started with. Right? Here, this is fault tolerant. So now that we are not afraid of RASA that much, and also we don't have, basically single point of failure here, even if you have a data center, that data center can be totally destroyed and we still be safe. So why not just go for the centralized thing? This is how the rest of the world works, is that everybody has a boss, bosses have a boss, and they have a boss, they have a boss. So that is how we will run the network. Right? So that is what is happening, is we are going for centralization where we were going for distributed before. Any questions about this? Any comments? And please ask questions, because then I will know where to go from here. So there are 4 confusion about SDN. When you read about SDN, you will find papers after papers after papers, and some of them may be wrong. And many of them are wrong. First of all, they confuse policies with control. Okay, I said centralized policies. I did not say centralized control. Separation of control plane. That's a confusion. SDN versus OpenFlow. OpenFlow was the first protocol that was designed by the people. Actually, SDN came later. OpenFlow came first. So what was happening was, Stanford University professors wanted to have a network in which they could experiment at the same time while it was being used by the real people. So they said, okay, we'll separate into two ways. And so they designed a protocol, OpenFlow, which separated the open control plane from data plane. And OpenFlow is a protocol which connects the two. And then somebody thought, if we can do this, we can do software-defined networking. And so it came from, so OpenFlow is the father of SDN, or mother of SDN, but it's not SDN. Okay? And then some people confuse that we need OpenFlow, and I will show you in a minute. OpenFlow is micromanagement. Basically what happens in OpenFlow is you send a table to every router or every switch, and the table is very detailed. It says if the header looks like this, then handle the packet this way, and the table is very big because the header could be millions of different ways. So you have a very big table, and you have to do that, and the routers have no other choice. They just have to go through table by table, and there could be actually many tables now. And so you match in the table, and then you see what the action is. You match in the table what the action is. So it's like micromanagement, exactly telling what to do. Right? So I have this cartoon which shows you what is the separation versus centralization. This is separation of control plane. Nobody else has any control. Means they have no brains. They cannot think. This is the only guy who can think, and then they have to follow. This is separation of control plane. This is centralization of policies. Here this guy tells that, okay, today we love China, and these guys will basically follow that line. Right? They will tell their employees, and they will tell their employees, and the whole America is suddenly loving China. Okay? So I'm just giving an example, but basically the idea, he doesn't tell them how to love China or what to do for China, nothing. He just tells the policy. Right? So the people confuse control, which is this, versus policy, which is this. In policies, people are left to think their own way as to how to get this thing done, because this is our policy today. right? So that is one difference. And this is micromanagement, because everybody has to do exactly as strictly as told, and they cannot use their brain. So SDN, so basically, this is currently what is going on in the SDN world, that SDN is easy if the control is centralized. If you have central control like they had in OpenFlow, then it is easy to do SDN, but it is not necessary. Distributed solutions may be required for fail-safe operations. So you could still do centralized policy control, but have distributed implementation. Okay, people are doing that. Complete removal of control plane may be harmful. So you do not want to completely remove the control plane like we saw in this cartoon here. You don't want to remove the brains of all the people. You want to use those brains. So, and in fact, we don't even know where the control plane begins, where it ends. Okay, so we don't even know exactly. SDN is easy with a standard southbound protocol like OpenFlow, but one protocol does not work. So a lot of people say if you don't do OpenFlow, you are not going to do SDN. And so the answer is one protocol is not required. You can design your own protocol, and lots of companies have designed it already. So right now, actually, it's kind of a known fact that many companies are not doing OpenFlow. So this was the case. Time at some point people were discussing this thing. For example, there is no one operating system, there is no one router, there is no one switch, and so everybody has their own choice. If industry finds an easier way to solve the same problem, they will use that. So people really, what they want to do is, they don't want to be told how to do it, they want to be told what needs to be done, and then let me do it. Right? I mean, you would want that, right? I mean, you don't want your boss to come and say, okay, like, write this code, this line, and that's it. Then what are you doing there? So that's the kind of thing here in SDN, is that really we don't want to just, and basically we tell what is our goal, and then people will find it. For example, some of you might remember ATM networks. So 10 years ago, the whole industry was working on ATM networks, and ATM had the good thing about that they had very good quality of service. And then suddenly it died because MPLS came about, which did not require changing anything but except putting some new protocols, and it gave the same features. So people will figure out how to do it with the minimum effort. So what is happening to SDN? SDN was invented in 2009 by a student at Stanford. Now that student formed a company called Nicira. He sold it for $1 billion, so he's rich now. He got paid well for that invention, and to VMware, and now I think he is just ABC, investing in different companies. But anyway, at that time, SDN was separation of control plane and data plane. So you had control plane, and then there was data plane. And there was centralization control. That's how he defined it at that time. Standard protocols between the planes, and he defined that there is open flow between these control plane and data. But this is not how it is today. If you go to Cisco, if you go to Juniper, if you go to other companies, they have their own way of defining SDN. So now, it is basically disaggregation of hardware and software. So now what we want to do is, what this gave us was that we really want to separate the hardware from the software. So you can take the same software and run on any hardware. And hardware is generally very standard nowadays. So you don't need to buy very specific hardware. And so that is one thing which has happened. And the software that runs on commodity hardware. So basically the hardware is very cheap and it is not specialized, it's commodity. Basically something that is produced in billions and millions, like a PC. Open source software. And that's another thing that is happening, is that all the software is open source. If it is not open source, we won't use it. So as you will see, there is open source SDN controller, and anything you want to do nowadays, there is open source for that. And controller replaced by the orchestrator. So we don't call it controller, we call it orchestrator, because this can basically, as we said, change the policy of the whole network sitting at one place. And centralization of policies. So this is not centralization of control, it's centralization of policies. So this is how it has finally turned out. And if you were to look around the industry, there are many different kinds of SDN. One is Open Daylight. So Open Daylight is a controller that was written by the industry. Again, open source means 20, 30 companies got together and wrote the controller. before this was another controller which was written by Stanford, and that was obviously using OpenFlow as the only protocol. But this Open Daylight uses maybe 50 different protocols, in case of OpenFlow, and it also uses OpenFlow also. So basically now it is totally open field. Is a multi-protocol southbound. Southbound means basically this is going south. This is orchestrator. This is hardware. You're going south. So that is southbound. By the way, there are not enough questions here, so I don't know what people are afraid of. They are not.
Generally, we are used to asking the last. Generally.
No, so don't ask at the end, because I really think it will be good for me to know where people have questions. Any questions so far?
One question.
Yeah, good. Yeah, start.
Deviating from
Yeah,
tradition. Now networks are all voice and data both are there.
yeah,
Now that is how the difference network what we are
yeah.
How it will happen in that?
Okay, so what is happening, voice versus data? Actually, the voice networks are going away. You just saw Reliance announced Geo. So everything is data. We have similar plans in US, where, you don't really, we don't pay for voice, by the way. In India, we have to pay by the minute for the voice, but I think this will go away. In US, there is no per minute charge for any voice by any carrier, right? So voice is basically data, and now it is taking time because we are used to certain kind of voice, which basically will get there by proper programming and other protocol changes. So the networks are really for data, and to support voice and video and other things, we still have to distinguish in the traffic, among the traffic, and that is much easier to do with software-defined networking than without, right? Previously, we were actually doing it by hardware, so we had a hardware which could handle only voice, and we had hardware which could only handle data. Now, that hardware is already gone, the voice hardware. So we are only left with this hardware which handles data, but we have to make it such that it can distinguish itself that this is voice bits. Now let us give it a priority somehow. Does that answer your question? Yeah? Okay. All right. So the second thing that is happening is that now you can buy bare metal switches. So there are switches which have no software on them. They are just hardware. Okay, and you get some software from somewhere else and put it on there, and you got a full router. Of course, the network operating system could be bought, or could be just open source. So here the switches you can buy from Dell, Edgecore, HP, Penguin, QCT, etc., and then you can get this software which is called ONI, and then you can get network operating system from all these different companies. So you get two things separately. Because of the SDN, software-defined networking, now the hardware is on one side and the software is on the other side. And you can buy them separately from different people and mix it. Then network virtualization and overlay, that is another form of SDN, and VMware is selling that. Basically, if you buy the VMware software, then they will somehow separate the hardware from software. And then ONF. ONF is the Open Networking Foundation. This is the Stanford group. They have their own version of SDN, which still insists on OpenFlow. But I think finally, I think they got away from that as well. And so really the first three are left. So in any way, all four provide you abstraction, which means the hardware doesn't matter, programmability, and centralization. Not centralization of control, centralization of policies. Yeah.
So how QoS will be affected because of this?
Yeah, right. So this makes QoS very easy, because now we can define the traffic in whatever way we want to define and tell the switches very fast. Basically, the thing is, previously, if I want to implement QoS, I have to go to each switch and program it. Each switch has a different way of changing things, right? Because one you bought from Cisco, one you bought from Juniper, and you can't talk to the same language to them, right? Now with this thing, you can just issue one command and say, okay, all right, when you see something like this, do this. And that goes to all the hardware and basically all the routers. So it's not only easy, but also very fast.
But main thing is like switch I have taken from one vendor, OS from another vendor, generally like Cisco.
Yeah, so these switches are somewhat standard. Yeah.
These two coupled, then only they are assuring data plane latency.
No, so the thing is, the switches, the hardware that you're buying is not specific to one software, particular software, first of all. So they are all somewhat standard. They look very similar to each other, except that some might have so much of stack space or buffer space or memory space and bigger processor, things like that. So otherwise, they are very similar. Yeah.
We looked about the southbound API you mentioned. So, but what about the mainly now the application talks to this framework?
My application talk to the controller.
Mainly your application has to demand the one-time network.
Yeah. So what you are talking about is what we call northbound. So applications are somewhere here, and they want to talk to the orchestrator and say, look, I have this application. For this application, I need this service. That is not defined yet.
What are the interfaces normally that's not standardized?
That's a problem right now. Yeah. And we'll talk about that. So that's actually what is happening, and we are actually working on that as well. So northbound right now is not a standard.
Congestion control code will be.
Congestion control can be taken care of here, because congestion control basically is again same thing, is that you can tell some traffic to go on this route, even if they are going A to B, you just tell them that, you go to this route because this one, and other traffic to go to another path, and another third path. So there are more possibilities. Previously, everybody discovered by their own, and everybody found the minimum cost path, same path, right? So there was congestion by design, right? Now, because of centralization, we can look at the whole thing and say, right now it is 5 o'clock, and there's big congestion on this road and that bridge, and so on and so forth. And so go here. So you get that kind of thing. So congestion control becomes very easy. Quality of service becomes very easy.
What are you doing now for this NPI? NPI is required for component interface.
And for what? For what? NPI.
NPI, not node interface.
I'm sorry, MPI?
NPI.
Not on interface. Okay, yeah.
What are you doing now?
So it will come in a minute. Actually, everybody has their own solution. I have my own solution. But let me say, one thing is that another trend that is happening is that clouds are becoming smaller. So previously, cloud meant you had to have a big data center, hundreds of computers, right? Now you don't, because now the computers have become so big that you can have 64 cores, 32 cores, 8 cores. So you can just create a cloud inside a computer. Okay? And so we have in our lab 6 clouds, basically 6 computers. Okay? And we are working on multi-cloud research, so we need these clouds. So basically, the clouds are like this. We can call them micro-cloud, just to be exact, but they use exactly the same software. You run OpenStack software, which is open source software to manage a cloud. We run OpenStack here. We download from the same place, and then we just run it on a single computer. Okay, the clouds have become smaller, and the number of VMs is increasing, right? So we do exactly the same thing that you would have done in a big data center. Every program is a virtual machine, and we move virtual machine from here to there and things like that. Okay, so we just exactly the same thing. Second trend is, if you remember when we started the web, we all wanted to get the web page very fast. So what they did was they made copies of the web page and put it everywhere. And that is called Content Distribution Network, CDN. Right? Now, we want to do the same thing with computation. If you want to compute something, then you want to be able to compute at every place. For example, when you speak to Siri and you say, find my, this number or that number, that has to be computed. Right? If it all went to California, it will be very slow. You want it to be computed right here. So that is what is happening. So the carriers are putting clouds on the tower. Okay? Now these are not data centers. These are single computers. But they are very powerful computers. Very powerful means I just bought last month 6 powerful computers for $600 each with 4 cores, the latest, whatever comes up. So they're not very expensive. So those are the things you can put on a tower very easily. Right? So every tower will have a data center and a cloud on it. It's a micro cloud. And then when you want to do something, first it will be computed here. And by the way, there is a standard being developed for this. It is called Mobile Edge Computing, MEC. Okay? So this is happening. MEC standard is happening. And sometimes you have bigger computation to be done. Then you send it to the regional data centers or local clouds. And so then you have to decide as to what job can be done locally, what can be done there, and so on and so forth. Right? So this is what we call multi-cloud hierarchy. There are clouds everywhere, and if you put clouds everywhere, and then basically we call it a fog, right? So that is what is called fog computing, is because you look at outside and there's a cloud right there, and on the ground, let's look at a fog. So the fog. So basically, when we do the computation, when we write an application, we have to worry about how to divide it among the clouds. And so this is being done by the carriers also. So all the carriers, and everybody understands carriers are like Verizon in America, AT&T, here I think Airtel and Vodafone and Reliance. They are going to basically put everything in a cloud. So here is the cloud. Previously they used to have very expensive hardware for everything, such as LTE, actually says, but IMS, EPC, BRAS. These are all the functions that they need to do in their network, which used to be very hardware centric. Now this is all software. All right, and these are all virtual machines. So they don't even need a data center, because they can just go to Amazon or somebody else who is providing the cloud services here and say, okay, like, please give me 5 VMs and put BRAS on one, EPC on the other, and IMS on the third one. And on the same data center, some other carrier can go and say, well, I also need 5 VMs and put me on there. So everybody wins in this game, because everybody has less expenses, less maintenance, and the cloud computing guy is very happy, and the carriers are very happy. This is called Network Function Virtualization. Network Function Virtualization, NFV. Network Function Virtualization, so all these appliances have become virtual, and so you get all the advantages of virtualizations, such as mobility. Mobility means that you can move the appliance. Suppose you want to move the IMS from here to there, you don't need a truck. You just move the VM, like this, transfer a file, and you're done. And service chaining, and then you can chain things, as you need. Like packet need to go from LTE to EPC to something, you can do that very easily. So multi-cloud is required for all these carriers. Now the question is, if the carriers can do this, why not anybody else do it? So banks someday will realize, they haven't realized it yet. Banks still have their own private data centers, because they have so much money, they don't really worry about it. But someday they will realize that they're wasting their money. They should just make it a VM and put it on Amazon or some other place. Okay, and then share with everybody else, right? So that would be called any function virtualization. And it doesn't have to be bank, it could be hospitals, it could be stock market people and educational institutions, you name it. So that is SV, basically function virtualization, right? And all these things, you could put on multiple clouds. And then what will happen is, for the software, then you will have a big app store. Basically, whatever you want to do, you just go to some place and buy a big piece of software. Right now, the software comes in very small pieces. Your apps are very small, $1.99. And I don't know, and most of them are free that we use. But these would be a little bit more expensive. These would be like, $1,099 or whatever, $999 or maybe $10,999. A lot of effort has gone into it, but still it will be 100 times cheaper than the hardware that they used to have. They used to come in millions of dollars, these telecom machines, right? So it will be still very cheaper. But so this is an idea that basically you could buy all the Cisco software, routing software, everything, on the App Store. And now here I think that nobody has done this yet. But I would not be surprised if it happens very soon, if somebody comes up with, okay, like, why do you have to go? And I told this to Cisco, you are in the right place to be really starting a networking App Store. If Apple can do it, Google can do it, so can you. So people will not go, and the brand name helps, right? Anyway, so this is what is going to have a very large scale software, right? So now I'm going to move past, because now we have done enough SDN. SDN, as I said, 2007, 8, something like that, so 8 years old. Not maybe 8 years old, maybe 5 years old, because 2008 was OpenFlow and 2011 was SDN. So AT&T has actually deployed SDN, and what they can do is, they're sitting at one place, they can control all these switches. And they call it Domain 2.0. And I don't know how they came up with the name Domain 2.0. But basically all that means is that they can control all the switches in their network sitting at one place. All right? And that is past. That they announced like 2-3 years ago. Now what we need to do is, we have so many clouds, because the micro clouds on every tower, clouds here, clouds there, that we need to really be able to control all those clouds sitting at one place. See, these things are not switches anymore, these are whole clouds. So we need a multi-cloud virtualization of the cloud. This is like SDN at the second level. Each cloud might have SDN inside it, but now we need to have this SDN over SDN, this second level SDN to control these little clouds.
Is there any redundancy in this architecture?
Of course. So the thing is, first of all, simply because you have a cloud, you have redundancy. In cloud, everything is virtual. So if you are running something here, the cloud goes away, you put it here, right? And generally, if you are inside the cloud, you will have some spare resources left. So if your one VM goes away, you got the second VM. Okay? So virtualization itself gives you redundancy.
But for the top layer.
Oh, operating system. So that is actually a common thing, is that you don't have one manager. You generally have a standby manager. So when the manager is sick, everybody is not on vacation, somebody else takes care of it. So same thing here, when you have a central controller or a central policy manager or central orchestrator, there is a standby.
Is there any distribution at that layer also?
So that's an unsolved problem in the sense that everybody has that, but it is not a standard. There is no standard. Just like northbound, this is called east and west. So there is no standard for east and west.
So what about security, sir?
Okay, security. So security is all there. In fact, it becomes better because, just with the traditional methods of encryptions and other things, we make sure that the clouds verify, validate all the commands they're getting. And so yes. So actually, that's a debate we can have, is that it makes it a little bit open to attacks, because once you have things on the network, they're open to attack. So security needs to be done, but then people like us are working on that. Actually, I have a research grant on security of multi-cloud. So in some sense, yes, security is a problem, and maybe people have solved it on a machine. Maybe some people are working on inside a cloud, how to be secure. And we are working on inter-cloud security.
Especially key management.
So there are some new issues here. So for example, if this cloud belongs to Amazon and this cloud belongs to Google, now you have some trouble here. Right? What you can trust to this and what you cannot trust to that. So yeah, that is something to be done. Alright, so we have this system actually. We have this system that we call Open ADN, Open Application Delivery Network, Multi-Cloud Management. And we have already written this whole piece of software. So you tell all these policies, and this platform will compute what we need to tell the network. And then it will tell different cloud, different things. So this is a cloud which is being managed by OpenStack, which is an open source software. This is an Amazon cloud which is using EC2. OpenDaylight is another piece of controller which only manages networks. So we have written drivers for each of them. So we didn't standardize anything. We didn't go to standards bodies. We just wrote the drivers. So when we talk to OpenStack, we speak their language. When we talk to OpenDaylight, we speak their language. When we talk to Amazon, we speak their language. And so now you see, you are talking about northbound. So this is all southbound. And actually this is different southbound because this is talking to the cloud, not talking to the switch. Each cloud has its own way of talking to their switches, which could be very different. We are just talking about the cloud management. And then inside the cloud, say for example, this one belongs to Amazon, whatever they want to use, they can use. Right? And then northbound for us is basically this we have developed our own. So the people who develop, they need different facilities, so there's interface for them. People who deploy, they have to put firewalls and other things. We call them architects. There's an interface for them. And the people who run this every day, we call them this administrators. They worry about the cost and the price and things going up and down. So there's another interface for them. So we have these three interfaces for northbound and many different interfaces for southbound. But again, this is at a cloud level, not at the device level. Yeah.
How is the load balancing across the multi-cloud?
Right. So basically, this is very complicated piece of software, and it has to follow several policies. It could say that, well, I want my load to be balanced across these two clouds, if you wanted to do that. Or you could say that, well, I really want to run on the free cloud here, OpenStack, but when it becomes overloaded, then give it to Amazon. So depending upon your policy, it will divide the load.
This policy is centralized or distributed? This load balance?
Okay, no, you specify. So whoever is running this application actually, so I'm going to show you next slide where you could run many applications. So whoever is running this application has a policy because they are paying the bill, right? So yeah, the policy is central, but it is specific to each application. So actually, I will show you, a slide is coming in a minute. Yeah.
So in this SDN architecture, do we have to replace all the hardware which don't have the capability of SDN protocol?
Right. So the question is, can I reuse the 10 years old router and then still do SDN? That could be a problem. Basically, many of the recently done routers can be converted from previous non-SDN to SDN. But if you have very, very old piece, maybe it will be very difficult.
For using the SDN architecture, anywhere you want some form of interface, right?
So there are two kinds of applications. We say greenfield and brownfield. Greenfield is when there's nothing and I'm putting a new network. Right? That obviously you can do very easily, buy the new equipment and you're all set. Brownfield is where you have something and now you want to put something new, there is some work to be done.
Can you take NBS as a component between the southbound interface and the driver, the device that
Yes, some people have done that. So basically the question is, can I just use as a device driver like we are doing here, cloud driver? Can I just do to each device something like that? Yeah, you can do that kind of thing. It is kind of a lot of work, but some people have done that. So here's an application for mobile healthcare. So here this guy is wearing a belt and suddenly the belt says that your blood pressure has gone up. It goes to the local cloud on the tower and it says, oh, the blood pressure is just too high, we need to call the doctor. The doctor is on a different cloud and the doctor looks at the numbers and says, no, we need to call the insurance company and the hospital, and everybody is on a different cloud. Right? In fact, insurance company might have many, many clouds, right? And the hospital may have many, many clouds. So the right cloud, right application, right part of the application has to run on the right cloud. All of that is done by this platform. This is called Multi-Cloud Mobile Application Deployment and Optimization Platform, MCAP. So this one does the policy. Who is setting the policy? The policy is being set by this person who is running this application, which happens to be medical application. And there could be another application running at the same time on the same clouds, maybe banking application, or maybe another medical application. They would have their different policy. Right? So, but this is only one central, for this application, this is the central point of policies.
Is there any priorities when you share the load?
Right. So the question is, when you are sharing with the other tenants, do you get any priority? That is actually specific to the cloud provider. So if you go to Amazon and you say, I want 3 VMs, the price is not fixed. If you pay $5, you get some VM. If you pay $10, you get a better VM, and better service. So yes, there is a priority, but that is inside the cloud mostly. However, we could put the priority between the clouds. We are just right now concentrating in our research, inter-cloud. So we do have priority that, okay, we want the cheapest one first, and then, somebody may say, no, I really want, higher priority or whatever. So, the priority among the different applications we don't worry about. We don't do it. Okay? But I'm sure at some point when you have a tenant, there are rules as to what you can do or what your other tenants can do. So that we don't have.
So regarding this SDN controller, do
Yeah.
you have any standards for that? Defined
Okay, so this one is actually inter-cloud controller. There are no standards. They are being developed right now. Actually, they are not really even developing the standard nowadays. All they are doing is developing the software straight, and that becomes the standard. So while we develop this thing, MCAD, the standards bodies are developing something very similar. Okay, I mean, we publish it, and people start. So there is Mano and other applications, and that's all we need. We don't need a standard. We need a software that we can use, and that becomes. So nowadays, that is another thing that is happening. Another trend, that instead of standards, we need open source software, and that becomes a de facto standard. Because every company has contributed to it. Right? It's open source. So most people are not going to the standards bodies; they are going to the open source forums. All right, now you guys are tactical gurus. So I'm not going to say much, here, and you have to decide your own as to what applications you can do. But I made up this slide once I talked to. Basically I talked to at a conference, MILCOM, which is military conference. So I just made this slide up, and I'm sure this is totally wrong. But basically, every soldier will have a cloud. Okay, if not today, tomorrow. And then, of course, you will have a cloud on every tower, on every plane, on every truck, and in every ship. Multiple clouds, right? So you will have a multi-cloud problem, right? Now, whatever applications you are running, you have to do what we are doing is basically decide a policy as to how, what the soldier's cloud can do, what needs to go to the plane, what needs to go here. All of those things have to be done. And in fact, if you have multiple missions going on at the same time, so this mission director using the same hardware piece, because they're just sharing the same hardware, same ship, same plane, so on and so forth. They will have their policies. So this is basically, we call it mission director A. He has his own global controller and giving commands to the same clouds through their local controllers. This is mission director B and giving the commands to this one. So this is basically, this allows multiple missions to share the same piece of hardware, same set of clouds. And so we actually developed this, and there are papers which you can read later on. And
Any case study specifically for a defense scenario?
no, actually, there is no case study for defense. Actually, basically what happened was at one point I was writing a proposal for defense project ARPA. So we thought of all this, but we didn't get funded. So we didn't do anything in this direction for defense. But very recently we got funded by NSF to do something similar for security. So we are working on security aspect, but not defense aspect.
So one more basic problem in defense, and that has been tactical.
Yeah.
You have computing resource which is less. Bandwidth is much less.
Yeah, no. So this is actually I forgot to mention this. I forgot to mention this. When you are doing inter-cloud, bandwidth is the bottleneck. In any of these scenarios, this is not the bottleneck. Computing power is going very fast, and it is already very fast, right? Even in your iPhone or your phone, you have a lot more power than whatever we used to have, right? So computing is not the problem. Problem is the link. And so when we do our optimization, that is the new thing, is how do we make the best use of the link? And same thing applies to tactical applications.
You have shown, sir, 5G. We are working on 1G right now in tactical area. So how do
Well, so here is one thing. I don't know why you're working on 1G, because in the United States, the technology, in the United States, the technology comes from the military. Everything, the latest is with the military, and then it becomes commercial. Once the military has paid the big bill, they pay millions of dollars for doing this little thing. Once it is done, then somebody starts a company and sells it to everybody else. So everything really starts from the military and then becomes commercial. Right? So I would be saying that 1G or 2G or 3G at this time, basically probably not best use of resources. So who is working on 5G? Of course, the military people are funding a lot of research in 5G, as well as of course the carriers who are going to make money out of it. Now 5G is more into the commercial domain anyway, but the military is funding a lot of research on wireless, which will be fed into 5G. All right. So we talked about multiple missions, And then there's the problem is that basically this is a mathematical problem that you have some application that you want to put on, you have some clouds. So how do you divide that? So this bin filling problem is, forever, for academics, we have this NP complete. This problem is NP complete. So we are developing solutions which are basically very realistic heuristics. And we have some papers on that. I would not go into detail. Then we are working on cloud security. So multi-cloud has its own security issues. So we just got some funding from NSF. And this is the one that we had done for DARPA actually, this proposal, but we didn't get funding. So we got it from NSF. So we are working on that little bit on the multi-cloud security. That brings me to the end of my talk, exactly 5 o'clock. And that is that 5 key points. First is that the STN is about abstracting the hardware and providing the programmability and centralization of policy. Remember the word policy I emphasized so many times, not control. Second thing is the clouds are getting smaller. And so the clouds will be everywhere. I have 5-6 clouds in my lab. And, we could be, I would not be surprised if our phones have start having some, cloud software in them, very soon. Multi-cloud application management system allows you to do the policy deployment and share with other tenants. And then it has important technical applications. And then service function problem, placement problem, which is the last problem I talked about, is that where you put what part of the application is NP complete. And WAN link is the bottleneck, actually, as I said before. So we have developed some solutions for that. Okay? Now, there are lots of papers. And so you will find it. And if you want these slides right now, just QR code, it will come down to your phone. Okay. Any questions? How do we manage reliability in case of? In case of the controller failure. Yeah. No. So the thing is, here I have shown you 2 controllers for 2 different applications. There is no reason that they could be managing the same application. The B could be on the standby. That's the whole orthogonal problem. Basically, how you do that, whether it is hot standby, whether it is cold standby, whether it is some other kind of standby, those problems have been studied in the past, right? So basically, so I'm just saying that most people who are working in this area, there are other people who are working on those things actually, who are just taking a general problem of how to do standby, and that will apply here.
But I think she's also asking about the reliability. Now that you're making it virtual software design,
Yeah.
how can you guarantee the reliability of the system? Not about hacking alone.
So I don't know whether hardware makes it any more reliable than software. I mean, if you are claiming that the hardware is more reliable than software, maybe, there's some data, something which I don't have myself. Maybe you guys have some data about the failure rates.
There are thousands of bugs still, but so that is the
I don't know, but I think that's a totally independent, again, orthogonal discussion to have. Any other questions? I know it is 5 o'clock on a Saturday. I really appreciate you guys staying here. It's only 4 o'clock. How come? Okay, then we got 1 more hour. I was thinking 5 o'clock. I don't know how. Okay. All right. Any questions?
So how data handoff from cloud to cloud on the mobile networks, like moving Internet of Vehicles kind of applications?
Yeah. So this happens every day, even today. It maybe not goes to one cloud, but basically, when you do any computation on your phone, it is really not done on your phone. It goes to the cloud. Okay. Siri is a good example. You speak and right away it seems to have figured out what you said, but that analysis of the waveform is actually done in the cloud. Right? And then you said search for this, and the search is done on the Google Cloud. And so first, the Apple Cloud translates this waveform to a text, and the text is sent to Google to give you the answer. So all this is happening right now. Huh? Now, Internet of Vehicles, a totally different topic. So now basically, yeah, right. So basically, in the case of when the vehicle's internet comes, right, then you are saying how the data will go from here. Okay, so yeah, right. Basically, every car will be a cloud for sure. Okay, every car will have compute power so that it can have some virtual machines here and there. And then how will it go from a compute car to car? There are lots of proposals right now. And I have a different lecture on VANET, which is VANET is Vehicle Area Network or something. But it is not firm yet. Those things are not solidified yet. And I don't know, as a military, basically what happens is, at least in the US, military doesn't have to wait for the standards. They just develop their own, they have a lot of money. And so they develop their own products, their own standards, and then the rest of the world just follows it. Same thing as Internet. Internet was developed by the military, DARPA, and then we are just using it. Right? ARPANET was free actually, and that's why it succeeded, because it was free. And we had, at that time I was working for Digital Equipment DECnet, and IBM was having some other net, and everybody had their net, but they were much more expensive. ARPANET was there, you just connect it and go and use it. So that's how it succeeded, TCP/IP. Okay? Thank you.